Hello everyone, welcome to the course on digital signal processing. This is lecture 1 and in this lecture we will see what are the ways to design the digital IIR filter. So first of all we will start with the filters. So filters basically are the system which allows the input signal to pass, and this filter basically consists of three different bands. First band is called as the pass band. So pass band is basically the range of frequencies which are allowed by the particular filter, and we have the stop band. So the stop band is again the range of frequencies where the filter is blocking the input signal. Similarly, we have the transition band, which is the frequency range between the pass band and the frequency band. So we'll start with the definition of filter first. So filter is generally a frequency selective network or a device. So signal having certain frequencies are passed, whereas signal having other frequencies are blocked or attenuated. So we are defining a filter by its frequency response, and the frequency response is given by h e raised to power j omega, this one. Whereas we have seen that the frequency response can be written in two different ways. One is called as a magnitude and the other one is called as a phase. So we have the magnitude plot and the phase plot. So now we have the definition for the pass band and the stop band. So the pass band, the range of frequencies that are passed through the filter, so they are called as pass band, whereas the frequencies which are blocked or attenuated are called as the stop band. So next is for the frequency in the pass band, the magnitude of amplitude, which is magnitude of h e raised to power j omega, is relatively large. Whereas we can say in the stop band, the magnitude of h e raised to power j omega is very small. We can see, we'll be seeing later on when we'll see the designing of IIR filters. So next is, let's say we have a case which is corresponding to the low pass filter. So we have in this particular figure the magnitude response of a low pass filter, and we have two kind of responses. One is the ideal response, we can see here, which is shown in the dotted line, whereas this practical low pass filter is shown with this particular shape. So we can say that this particular range of frequencies which are allowed, where the gain is very high, this is called as the pass band, whereas the range of frequencies which are blocked or attenuated, they are called as stop band, this particular band, and in between we have the transition band. So to the left we have the magnitude response of the ideal and the practical low pass filter, whereas to the right we have the magnitude response of an ideal low pass filter and a typical Butterworth response. Later on we'll see the classification of IIR filters. They are classified as the Butterworth and the Chebyshev filter. So the property of the Butterworth filter is that they are having a flat, maximally flat type of response. So here we can see that in the pass band we have the magnitude A and A1. Similarly in the stop band also we have the attenuation which is this, like this. So it is basically the range of attenuation or the amplitude, you can say the magnitude of h e raised to power j omega. So we have defined the cutoff frequencies. Cutoff frequency means the frequency at which the gain reduces to 3 dB or it reaches to 1/√2 times the maximum value. So that is the corresponding definition for the cutoff frequency of a filter. So further we'll classify the filters as IIR and FIR. So IIR stands for infinite impulse response, whereas FIR stands for finite impulse response. Later on we'll see what are the differences between these IIR and FIR filters. So first of all, this IR filters, they generally have the feedback connections because the present output depends on the past output as well as the inputs. So if they are depending upon the past output, that means definitely there has to be some feedback connection. So they are also called as recursive filters. So very important points, key points, that IR filters are having the feedback connections. Also they are also known as the recursive filters, whereas this FIR filters don't have a feedback connection because they rely on the present output depends upon the past or present value of input. Our whole system, FIR and IR, they are not depending upon the future value of input because the system will be non-causal, and we are already aware that non-causal systems are not physically realizable. So the key points regarding this FIR is that FIR doesn't have the feedback, so that's why they are also known as non-recursive filters, like this. So IR filters are designed by considering all the infinite samples of the impulse response Hn, whereas FIR filters are having a finite impulse response, means Hn is of finite duration. So how can we get the frequency response? If we take the let's say the impulse response also can be obtained with the help of the frequency response if we are taking the inverse Fourier transform. So there are several techniques to design those IR filters. So the methodology behind the designing of the filter is designing the digital filter is, first of all we'll design the filter in the analog domain, and after that we will be using some transformation techniques so that the analog domain filter can be converted into a corresponding digital domain. Also we will be focusing upon the properties that if an analog system is stable, so the corresponding digital filter also has to be stable. So later on we will see what are various transformation techniques to convert an analog low pass filter into some band pass filter, high pass filter or band reject filter. So we have a small comparison over here. So first of all, this FIR is a finite impulse response, whereas IR is an infinite impulse response. Nature we are already talked about, that FIR are non-recursive filters, whereas the FIR this IR filters or the IR systems are recursive. Computational efficiency, the FIR is having a less computational efficiency as compared to the IR system. Now the usage, IR filters are quite easy to deploy, whereas this FIR is a bit difficult. Regarding the feedback, so as we are already aware that recursive systems are having the feedback because the present output depend upon the past output. So the feedback is present in case of IR, whereas it is absent in case of FIR. Also regarding this stability, that FIR systems are inherently stable, whereas this IR filters are less stable as compared to the FIR. So again we have the definitions for the recursive and non-recursive over here. Delay offered, comparatively low delay is offered in case of IIR filters as compared to the FIR. Further memory requirement, while we are realizing the structures for this FIR and IIR, so it has been seen that FIR filters require less memory as compared to the FIR because also they are less, FIR filters are less sensitive, whereas the IR are comparatively more sensitive. So here we have a comparison chart, so that basically shows that what are the basic comparison points regarding this FIR and IR. So next is we just directly move to the IR filter design technique. So basically there are three ways to design a IR filter. So first one is called as approximation of derivative. The second one is called as a impulse invariance transformation technique, and the third one is called as a bilinear transformation. So the approximation of derivative, this method is also used for the designing of IR filters but at this particular stage we are starting with the impulse invariance transformation technique. So what this transformation is, let's say if we have the samples, if we have the impulse response of the, let's say, analog filter, so we'll be taking the samples. As we can see here, in this technique, the desired impulse response of the digital filter is obtained by taking the uniform samples of the impulse response of the equivalent analog filter. So Hn is nothing but H of Nt, where T is called as a sampling time. So the transformation technique can be explained, can be well understood if we'll assume an analog filter transfer function having some distinct poles or simple poles, which is, let's say, HAS equals to summation I equal to 1 to m AI divided by S minus Pi. So the impulse response specified from this above equation can be obtained by taking the inverse Laplace transform. So the inverse Laplace transform for this particular transfer function is nothing but HAT, which can be obtained by using the inverse Laplace transform. So if we are already aware 1 by S plus A, the corresponding inverse Laplace transform will be e raised to power minus AT. The transform will be e raised to power minus AT and u of t. So if we can see that AI divided by S minus Pi, the inverse transform will be AI e raised to power PIT and UT. Since A is corresponding to the analog filter, so u of AT is a unit step function in the continuous domain. So now how can we obtain the impulse response of the digital filter? We'll be taking the samples. So instead of T, in this equation number 3, we'll be replacing NT and we'll be converting this analog filter into a digital domain. So the impulse response Hn can be obtained by taking the uniform samples. So we can see this equation number 4, this Hn equals to HANT. Instead of HT, we put T equal to NT in the last equation. So we have again summation AI e raised to power Pi NT and u of NT. So from this equation number 4, the system function Hz for a digital filter can be obtained by taking the Z transform of equation number 4. So the Z transform we are already aware, the equation for Z transform is Hz equal to summation n equals to minus infinite to infinite h of n z raised to power minus n. So how this Hz is in this particular form, as we can note down here that since our system is a causal system, that means the system will be right sided. So the system is right sided. So what happened? The summation has to be from n equal to 0 to infinite, or we are already aware that how to check the causality of a impulse response, that Hn equals to 0, for all n less than 0. This is a property for the causality of the impulse response. So if we are assuming that the system is causal, because we have to implement this filter, we have to realize this particular filter with the help of some structures. So it has to be causal one. So the summation can be converted from minus infinite to infinite is 0 to infinite only, and we'll be taking the Z transform of equation number 4. So you can see in equation number 5, how can we further solve this? How can we obtain Hz? We just want to swap these summations, and what we are getting by moving these summations, we have summation n equal to 0 to infinite ai e raised to power pi nt and u of t z raised to power minus n. So again u of t we have we are having e raised to power n un. So if you remember, what is a Z transform? What is a Z transform for a raised to power n un? So the transform is a bit easy, 1 by 1 minus a z inverse. So we are going to use, this is nothing but our a raised to power n. So we have 1 by, or we can say this is actually e raised to power pint is nothing but a. We can compare this and we are getting ai divided by 1 minus e raised to power pit and z inverse. And with this particular summation I equal to 1 to m. So this is, we are getting the impulse response of the digital filter. Now how can we map this S domain, the analog domain, to Z domain? So if we'll compare our first equation, so we are having some simple poles which is some ai divided by S minus pi type, and in the digital domain we are getting 1 by 1 minus e raised to power pit z inverse. So this is the mapping formula. So we have to obtain how this S plane got mapped to the Z plane, because this S plane, this is an analog domain, and corresponding this analog domain filter is basically transformed to a digital filter using with the help of impulse invariance transformation technique. So if we can see, now we are going to basically see what are the relationship between the poles of the analog and the digital, this transfer function we can say. So if the mapping factor z equals to e raised to power st, we are already aware that this is a mapping factor, so that we can convert a S domain into the Z domain. So if we'll put Z is in digital domain, S is in analog domain. So instead of S, we are putting S equal to sigma plus j ohm. Ohm is the in analog domain, whereas Z is in digital domain. So Z equals to R e raised to power j omega. So in equation, let's say equation number 6 over here, we are going to use this S and Z. So if we'll compare this equation number 7 to in both the sides, we can say that the real part is R over here. Here the real part is e raised to power j sigma t, whereas this e raised to power j omega can be compared with e raised to power j ohm t. So I'm getting the result. One is regarding the magnitude and one is regarding the phase. So this equation, this next equation, these two equations are very, very helpful in explaining the stability of a digital filter. So let's say we'll start with the first equation, which is R equals to e raised to power sigma t. So if sigma is less than 0, means if we have the S plane, complex S plane, and if we have the sigma less than 0, so we can see here, if sigma is less than 0, e raised to power some negative quantity, so definitely this R, the radius of the circle, which is in Z domain, is the region inside the unit circle. This one, this area is mapped inside the unit circle R. Whereas if sigma is greater than 0, that means this is a region which is to the right hand side of S plane. So this region is mapped outside the unit circle, we can see in the Z domain. Also we can see that if sigma equals to 0, so e raised to power 0 is nothing but 1. So if R equal to 1, it shows that we have the radius equal to 1. So means this entire j ohm axis, right, will be mapped where onto the unit circle, means this particular, like this, right. So the entire frequencies in the analog domain, which is from minus infinite to infinite, got mapped onto the unit circle in the Z domain. This is a very, very important property. So first of all, we are talking about the stability of the filter. That means if the analog filter at the analog system is stable means the poles are lying in the left hand side of S plane. So correspondingly, the digital filter is also the stable one. So this is a very key important point. Next is the mapping regarding the frequency. So as we can see that from our last equation, that omega equals to O multiplied by T. That means if we'll try to solve, if we'll put the values over here, ohm equals to O multiplied by T. So if ohm vary from 0 to infinite, let's say we'll just mark this value, this is pi by T. So if pi by T will put it over here, so I'm getting the value is pi. So corresponding frequency in the digital domain will be pi. Whereas if we'll put minus of pi by T, so I'm getting omega equals to minus pi. So let's say this is pi, 0 to pi and 0 to minus pi. So the entire range of frequencies in digital domain has been considered. So the frequencies are basically lying between minus pi to pi, like this. So beyond this, if you put 3 pi by T, so 3 pi by T is nothing but pi plus pi by T. Or you can say this is pi plus 2 pi. So pi plus 2 pi means this is pi and again 2 pi, means again we are landing in the same position over here. So what happened? We can say the mapping of S plane to Z plane is not 1 to 1. It's called as many to one mapping. It's not 1 to 1, it is called as many to one mapping. Means we can say that the entire if we'll see that the analog domain minus pi by T to pi by T analog frequencies are mapped between minus pi to pi in the digital domain. But further, from pi by T to 3 pi by T also they are mapping in the same region, which is again minus pi to pi. That means this is called as, this is many to one mapping, which is nothing but, we are already aware about this particular formula, right? It is let's say intermixing of frequencies, right? So we can say this creates a aliasing due to the sampling of the impulse response. So aliasing is highly not tolerable because we have several frequencies superimposed on each other that will definitely create some problem. Okay, so this is a drawback for this particular method. Regarding the stability there is no issue, but regarding this frequencies will be having some issue. So one further key point, that for the low frequencies we can say, the mapping is quite clear, but for higher frequencies they are also mapped in the same range. So that means this particular technique is not suitable for designing a high pass filter or some band reject filter. So only for low pass filter this method can be used, whereas this method cannot be used for designing the high pass filter. So we have a summary over here in 3 different ways. So how we can transform digital analog filter into the corresponding digital filter. So these are the identity also. We can prove these 3 identities by our basic method. The method says that if we have HS, so just take the inverse Laplace transform and try to obtain HT. Once HT is known using inverse Laplace transform, just put T equals to NT because we are taking the samples. So if we are putting T equal to NT, I'll be having H of NT. So H of NT is nothing but H of N. So once the impulse response of digital filter is known, we can have the system function. We can have the system function from the impulse response of the digital filter. So this is the basic, you can say the methods, basic methodology we are following in the impulse invariance transformation technique. This is also called as a general method. any numerical can be explained, any numerical can be solved by this particular approach, or this can also be used directly. So let's say if we have the first question that convert this analog filter into the corresponding digital domain. So in the digital domain, the method was quite easy, that this is somewhat the transfer function for a low pass filter. We will see later on how can we check this. So basically we have to use the impulse invariance transformation technique and assuming t equal to 1 second, and I have to calculate the corresponding system function for the analog filter. So the method, general method is easy, and also we can directly use the property what we have learned. So if we can see, the general method is, if we compare with our equations, equation number 2, s plus a divided by s plus a whole square plus b square. So before that, I just want to explain this numerical. If we use our basic method. So the basic method, s divided by s plus s square plus b square. If you remember, the Laplace inverse will be cos of bt. So let's say if we have s plus a divided by s plus a whole square plus b square. So the corresponding inverse Laplace transform will be e raised to power minus at and cos of bt, like this. So for this particular equation, we are getting the inverse impulse response ht, which is e raised to power minus 0.2 t and cos of 3t, like this. So cos of 3t. So this is called as an impulse response. Now how we can, we are having ut also over here. So from ht I can have hn by putting t equals to nts. So h of nts is e raised to power minus 0.2 nt cos of 3 nt and u of nt. In the next step, just transform this cos of 3 nt, just convert into the exponential form, e raised to power 3 nt plus e raised to power j3 nt plus e raised to power minus j3 nt divided by 2, and we'll be having the impulse response. This is h of n. So if h of n is known, so we can easily convert this h of n into the corresponding system function hz. So this is the basic way to solve this type of numericals. So if we directly use the property, you can see over here, that we have the system function hz, and finally we'll put t equals to 1 second, and I'll be having the impulse response of our digital filter. Similarly, we have a different question. Now we can clearly see this is quite important, because this ha of s, this transfer function, is not available in a standard form. So the method behind is, we need to convert this into a standard form by taking the partial fraction. So if we convert this into the partial fraction, so I'll be having, let's say this is equation number 1. So the basic method again remains same. Either we can calculate the corresponding impulse response, or we can convert these h1 or h2 in terms of a standard form, like this, whatever we have converted over here. So once we convert it into a standard form, we can directly use the relations, this equation number 2 and equation number 3, and I'll be having the impulse response, I'll be having the system function hz from the analog transfer function h of s, and by putting again t equal to 1 second, I can have the overall system function for a digital filter. So this is the final answer. What are the limitations? We have already talked about that impulse impedance transformation technique is basically many to one mapping, and many to one mapping means the higher frequencies are mapped in the same range of frequencies, which is minus pi to pi. So this is also called as a aliasing effect. So this aliasing effect, this many to one mapping is basically it can be basically overcome in our next method. We will see in the next lecture, that is called as bilinear transformation technique. So these are the further references. Thank you.